In this lecture, we're going to talk about local search algorithms. Local search algorithms can be thought of as a heuristic that's going to improve our solution incrementally. Here we have some solution. Unlike in a greedy solution, we're not going to start with an empty one. We're going to start with any feasible solution. From this feasible solution, we're going to make a local move to move to another feasible solution. In this case, we're going to look at the vertex cover problem. Initially, we start with a vertex cover that's feasible, marked by these blue vertices. Then we're going to pick a vertex. In this case, we pick this vertex, and we switch its state. We move it from the cover. When we remove it from the cover, we have to add some of its adjacent nodes to the cover in order to retain a feasible solution. But when we add these additional vertices to our cover, we can potentially remove some of the adjacent vertices. In particular, this vertex here can be removed from our cover and still retain feasibility. In the case of the vertex cover problem, this local move is not just removing this vertex, as we did initially, but adding all these other vertices, in some sense cascading out. After we do this local move, we have another feasible solution. In this case, we move from a feasible solution with 4 points in our vertex cover to a feasible solution here with 3 points in our vertex cover. It turns out that this is actually optimal. The local search algorithm is going to take this general form. We start with a feasible solution, we take a local move, and we move to another feasible solution. The details of the local move are usually very tricky to work out. In the case of the vertex cover problem, we're going to work them out just now. The hard part of a local search algorithm is to work out exactly how we take a local move. In the case of the vertex cover problem, we just saw an idea of how we're going to make a local move. We take a vertex, we switch its states, and then we cascade out from it. To make that more precise, so that we can actually write some code, we're going to make it a little bit more formal. So to make a local move, first we're going to pick some vertex in C. We're going to remove that vertex from our cover, and we're going to add that vertex to our set of touched elements. We're going to denote the touched elements by a set T. Then, for every touched element, we look at all the edges that are emanating from these touched elements. If we look at a particular edge, UV, there can be two different potential states it can be in. The first is that our element U is in one of our touched elements, and both U and V are in the cover. That is, U is a touched element, and we've added it to the cover. V is an untouched element that's already in the cover. In this case, we're going to add V to our set of touched elements. We're now going to touch this vertex V, and we're going to remove V from our set C. The idea here is that because we've added an element in our local move to our cover, and this edge is now doubly covered, we can remove this vertex and still retain a feasible cover, at least for the touched vertices. The other state is if our U is a touched vertex, but that both U and V aren't in our cover. In this case, we have to add V to our cover. That's because this edge is currently uncovered, and if we don't add V to our cover, then this edge will never be covered. In this case, the picture, or the idea, is a little bit different. We have some vertex that's touched, and when we touch this next vertex, we're forced to add it to our cover. There are 2 other cases where both U and V are in alternating sets, but in this case, we don't make any moves. All we do is we expand our set of touched nodes. You can work out those details on your own. In the case of the local search algorithm, we continue doing this set of touched vertices until we've touched every vertex in our graph. We stop when there's no more moves to make. A local move is defined by executing this entire procedure. We start by picking some vertex and then cascade out through the entire graph until every vertex is touched. You can see that in this case, the local move is actually quite complicated. Now that we have a vague idea of what a local search algorithm is, we can state what the local search algorithm is in general. In a local search algorithm, we start with some feasible solution. Finding this feasible solution can sometimes be difficult, but occasionally it's very easy. In the case of the vertex cover problem, for example, we can start by including every vertex in our vertex cover. Once we have a feasible solution in hand, we make a local move. The important point of this local move is that whatever we do retains feasibility. That is, after we make a local move, we'll retain a feasible solution. That is, we'll move from a feasible solution to another feasible solution. In the vertex cover, there were a lot of complications, and after we touch a vertex, we have to cascade outwards. All of this cascading is there just so that we can make sure that we retain feasibility. After we make our local move, we'll have another feasible solution. If our solution improves, then we keep this new solution. That is, we keep it as our new incumbent feasible solution. However, if our solution doesn't improve, then we go ahead and we try another one. In the case of the vertex cover, trying another local move is selecting another vertex to start our cascade from. Our local searcher algorithm is going to terminate if we're at some feasible solution where no local improving move is going to improve our solution. That is, we've tried all the possibilities, and every possibility results in a solution that has either worse or the same quality. At this point, we terminate the algorithm and we output the feasible solution that we have in hand. This is the idea of the local search algorithm. Of course, the details are always important, and the details are going to change from problem to problem. We saw that in the vertex cover problem, actually developing a local search algorithm can be a little bit challenging.